Welcome back to General Relativity. Today's lecture is about gravitational waves. I promised this at the end of the last lecture. To begin, we just recall our linearized Einstein field equations. These were Gij equals minus a half box h bar ij equals 8 pi g over c to the 4 Tij. And we consider these equations now in vacuum. We set Tij to be 0, which means we work in vacuum. This is similar to discussing electromagnetic waves, and to make the subsequent discussion as easy as possible, let us consider a wave. We don't know whether it's a wave yet, but let us consider a solution, shall we say, a wave stroke solution. H bar ij, which only depends on time t and one of the spatial coordinates. And that spatial coordinate we choose this to be the z direction. In this case, our operation box hij over bar becomes minus the second time derivative plus the second derivative into the z direction acting on hij. This is very similar to the wave equation that you might have seen when you studied, for instance, a guitar string, where this is then the direction along the guitar string, and you have simply a one-dimensional wave equation. The only difference here is that this is a tensor-valued equation. Which is, or let's say this is a wave equation we can actually put a 0 here on the right hand side because we already said we are working in the vacuum. This is a wave equation for the components of h bar ij. In general, these are 10 wave equations, and these correspond, so the solutions in a sense correspond to waves traveling in the z direction. So we'll just make a little note here. We note similar to wave equations seen when studying for instance sound waves, elastic waves. The elastic ones would be the ones on a guitar string, for instance, or electromagnetic waves. And the other thing we immediately notice that we know the speed of those waves, the propagation speed of our GR waves, so gravitational waves or general relativity waves, is c, the speed of light. Which follows immediately from this factor of 1 over c squared here in front of the second derivative with respect to time. Sometimes this is put here. It depends on the conventions that you have chosen previously when studying the wave equation. So you sometimes have the propagation speed squared here, or sometimes it's over here. This has one important implication immediately for the study of gravitational waves. Generally, they are emitted when some, let's call it, violent astrophysical event takes place. So something that has a lot of energy and that can potentially emit a gravitational wave that is quite strong enough for us to detect it. This is usually happening. Obviously, if this is a violent event, usually that will also has an electromagnetic signal, or you can see something. You can see that something is happening astrophysically, and this then emits a gravitational wave. You know that electromagnetic waves, these guys here, are traveling with the speed of light, and if our gravitational waves also travel with the speed of light, you would expect these different signals to reach you pretty much at the same time, with maybe very, very small differences, which can hopefully be explained by the processes that underlie the generation of these waves. So that is an important observational fact, that electromagnetic and gravitational waves, at least in general relativity, travel at the speed of light. How do we solve an equation of this type? The easiest thing to do is write down an ansatz. This ansatz is a wave ansatz which is tensor valued. So to construct a wave solution or wave-like solution, to construct wave-like solutions, we begin with the ansatz h over bar ij. We have here an hoppala. We have here an aij, and here we write cosine omega z minus t. Let me tell you what all the quantities are that I've just introduced. Aij are some tensorial amplitudes. Hence the name A for amplitude. You know that every wave that you study comes with an amplitude. These are obviously constant, or we assume them to be constant. And something you can almost interpret this like a frequency or wave number, but this is also a constant. And in this choice, we have, these are waves. These are waves traveling in the positive z direction. Before we discuss the properties of these solutions, let us have a quick look whether they actually satisfy the Einstein field equations or our linearized Einstein field equations. Let us check that h over bar ij satisfies the linearized field equations. All we do is we compute d over dt, h over bar ij. We assume that the amplitudes are constant, the omega is constant. If we differentiate with respect to t, we get hence our amplitudes out here, ij. If we differentiate with respect to t, we get an omega out and a minus sign because of the chain rule, but cosine differentiates to minus sign. Hence, we get an omega out and here sine omega z minus t. If we differentiate with respect to time once more, ij, aij, we get another omega out and another minus sign. Minus omega, and sine differentiates to cosine. Which is, if we compare with our ansatz up here, we are exactly back to h over bar ij, but with the minus omega squared. We do the same with the z derivative. There's no minus sign coming out when we differentiate, which means we get here a minus, and the minus comes from the fact that the cosine differentiates to minus sign. Differentiate once more. aij. This time we get just an omega out cosine omega z minus t. And we get again minus omega squared h bar ij. Which then implies the following: d squared dt squared with the minus sign plus d squared over dz squared hij over bar, which gives us this guy here. You see there's a minus sign here, so we get omega squared hij minus omega squared h bar ij, which is 0. And I should probably say something here. You see, I just dropped the factor of c squared here. If I had a factor of c in front of the t, this would again be consistent. So to make our life easier, we set c to be 1 to get rid of the speed of light in these equations. We can reinstate it in the end if we really need it. So what we have just shown that this H indeed satisfies the linearized wave equation. Next, if we have a look at our ansatz, our wave, or our wave ansatz, contains the amplitudes Aij. Aij must be symmetric because H is symmetric. Hij is rank 2. We know that anyway. It's rank 2 and symmetric. So contains, or has, just say has 10 independent components in general. Just like our metric tensor has, or just like H has 10 independent components because it is symmetric, rank 2, and we work in 4 dimensions. However, recall, we could find coordinates and we assumed that we are working in these coordinates. We could find coordinates where H, A, B, or Ij, I think I'm sticking to Ij now, satisfies partial IH over bar Ij equals 0. And we showed we had the freedom, the coordinate freedom to make this work. This, of course, restricts the number of components of Aij. So in general, we have 10, and then we subtract 4, which come from this condition, which means at most we will have now 6 conditions. Let's have a more closer look at this. Let us briefly consider a more general wave ansatz. In principle, we could have started with this more general ansatz, but I like to keep the discussion slightly easier in this respect. So it makes sense not to start with the generic ansatz here, Ij, and I'm having all upper indices for a moment. Cosine Ks xs, where our are just our usual coordinates t, x, y, z. And Ks is a wave vector. Or wave covector or contravariant vector, which we assume to be constant. And then, obviously, I could have started with this general ansatz here, but if we're using the slightly more general ansatz, then if we have a look at this gauge condition over bar ij, partial I, this then acts on all of this here, ksxs. We know that the aij's are constant. We can pull them out. If we differentiate once with respect to x by the chain rule, we get an ks out. And because we are differentiating with respect to I, we obviously here get effectively a delta out. So what one gets out here is a ki by the chain rule. Cosine becomes, of course, when you differentiate minus sign, and then you get your function back, ksxs. Which means dih over bar ij equals 0 is equivalent to saying that ki aij equals 0. What I'm trying to say here is, if you think about this condition here, which came from a coordinate transformation, if we had looked at a more general wave, you see here again that we can now have 4 equations that the aij have to satisfy. And these 4 equations again reduce the number of independent components. This also shows that aij has at most 6 independent components. We can reduce the number of components even further. And this is quite neat in the context of gravitational waves. So recall that the way we introduced our prime coordinate system, where we then dropped the primes, we ended up with an equation where partial I h ij over bar prime was equal to partial I h ij over bar minus box xi. Which means we can now do the following. However, we can still make infinitesimal coordinate transformations such that similar to before, we have xi x prime I minus some epsilon I. These are coordinates, functions of the prime coordinates with, this is the crucial bit, box psi I equals 0. Remember that what I've just said is our gauge condition was that this object here is, well, the same object with or without prime minus box xi, which meant we could choose box xi such that it was h. However, if we now make this transformation, assuming that box epsilon is 0, then this transformation obviously doesn't affect the gauge, which is what motivates this. This leaves our, I put this in quotation mark, our Lorentz gauge invariant, because what we had was this one, prime AB, partial A, HAB minus box epsilon I, which was the equation we derived earlier, which gave rise to our choice of gauge, which means if we make a coordinate transformation such that box epsilon itself is 0, then you see that this condition is unaffected by this. And this means in this particular case, since epsilon I has again 4 components, we can eliminate 4 more components of Aij, which means if we count this all through, we started with 10 components, we take 4 away by our coordinate transformations that fix the gauge, then we have 4 more coordinate transformations we can make that leave the gauge invariant, which means we start with 10, you could say degrees of freedom, but with 10 components, so we reduce 4 and then we reduce another 4. Hence, Aij has only 2 independent physical degrees of freedom. And to link our slightly more general discussion back with our discussion we started with, so our choice for K was Ks, and that had components minus omega 0, 0, omega. For this choice, we had the solution that is given up here. Oh, that's quite high up. I better write this down again. This guy here. So I'll just write this down once more. So our choice for this Ks was that particular vector. And we had h over bar ij, aij cosine omega z minus t. And the next result, I won't show this in full detail. One can choose our epsilon i's such that the gravitational wave solution is given by the following expression. I'm now writing this with upper indices. h bar ij equals we have zeros here, and it is conventional to call this component A plus. This component is called minus A plus. This component is called A cross. And this component is called A cross. And here we have our cosine omega z minus t. If you now do a simple counting of independent components, there are clearly only two A plus and A cross. And all the rest is either zero or related to A plus and A cross. And this gauge is very common in general relativity. It has a special name. This particular gauge is called the transverse traceless gauge. And this is because the wave travels along the z direction, but if you look at this metric perturbation, the metric perturbation is actually zero in a sense along the z direction. It is only non-zero in the x-y directions, which means you have the effect that objects experience a deviation from their regular position only along the x and y directions. And objects distort along the x and y directions only. I'll draw you out a few pictures at some point later so you can see what this wave actually does. And if you think about this wave, xy, the xy directions, they are transverse to the z direction. And you know when you have waves, you can have transverse waves and longitudinal waves. So these are our transverse waves where the distortion is perpendicular to the direction of propagation. And traceless, the other word that enters the gauge, traceless refers to the fact that the matrix Aij is trace-free or traceless. You see this simply by adding up the diagonal components. You have 0, A plus minus A plus 0. Hence it is trace-free. In the next lecture, I will then show you how you can understand the effect of a gravitational wave when it acts on a set of test particles. And this is quite nice because we can use the geodesic deviation equation to derive this, which is one of the other ingredients that were required in our construction of general relativity.